Hi everyone, Dr. Burns here with our next lesson in our chapter on acids and bases. Today in this lesson we are going to be talking about weak acids and weak bases and how we are able to solve for the pH and the pOH of those solutions. Now, as I mentioned in our previous lesson when we were talking about strong acids and strong bases, weak acids and weak bases only partially dissociate when they are in solution. So when we're working with weak acids or weak bases, we cannot simply use its original concentration to find the pH or the pOH like we did with strong acids and strong bases, as we saw in our previous lessons. Weak acids only partially dissociate in solution, meaning that their H plus concentrations or their OH minus concentrations will depend on the extent of the dissociation. Because as you recall, the H plus, which we also can call the H3O plus, remember those are interchangeable depending on if we have water in our reaction or not, if we show it in our balanced chemical equation. Those are interchangeable. We use those concentrations to find the pH or the pOH. But unlike strong acids, we don't know how that H plus concentration or that OH minus concentration is going to be in solution since there's only a partial dissociation. Therefore, we have to use alternative methods in order to find the concentrations of H plus or OH minus at equilibrium when a weak acid or a base is in solution. So let's talk about weak acids first. So when we're looking at a weak acid reaction, the ionization of a weak monoprotic acid, meaning it only has one proton to give away, which we are going to denote here as HA, in water is represented by the following reaction. Now again, if we don't want to have water in our reaction, we can write this as HA is in equilibrium with H plus and A minus. Okay, so you can see there that the H3O plus and the H plus are interchangeable depending on if we show water in our reaction or not. Now, weak acids as well as weak bases are going to be in an equilibrium because of that partial dissociation of that hydrogen ion. So we show this with our equilibrium arrows. Because this is an equilibrium, we have to have an equilibrium constant K. We've introduced the equilibrium constant K for water previously and discussed momentarily about that of an acid. So the equilibrium constant for a weak acid is represented as Ka, which is the acid ionization constant, is equal to the concentration of H3O plus times the concentration of A minus over the concentration, I'm missing my concentration there, of our original weak acid. You'll note that water is not present in our Ka expression because water is a liquid. Okay, so this is why we can sometimes omit water from these types of reactions because it's not going to contribute to the equilibrium because it's a liquid that does not have a concentration. So if we used the other version of our weak acid dissociation, we could rewrite Ka in a very similar way where we have the concentration now of H plus and A minus all over the concentration of our weak acid originally. So they're very similar, again the only difference coming from H3O plus and H plus, which we know are interchangeable, and that's just if we consider water or not. So the Ka values for any weak acid can be found in, I believe it's Appendix 4 of your textbook. So those are known values, known constants for all of our weak acids and weak bases, which we'll talk about specifically for bases here later in this lecture. But you can find those values in Appendix 4. So the larger the value of Ka, the stronger the acid is going to be. And that makes sense because we said that our strongest acids, the strong acids, the 7 strong acids that we need to memorize, they don't even have a Ka because they're not in equilibrium. So that means that their Kas are essentially infinite because they are not in an equilibrium. So the higher that Ka value, the stronger the acid is going to be. Now, when we're faced with a weak acid problem where we need to find Ka or pH, okay, these weak acids typically have Ka values that are very small. And as we know, if we're in equilibrium and we have an equilibrium constant that is small, that is going to simplify our calculations when we're working with these weak acids specifically. So remember, weak acids and weak bases are in equilibrium. So let's put a weak there because strong acids are not. So that's the important word that's missing there. Weak acids and weak bases are in equilibrium. So solving for anything in equilibrium, any concentrations or anything like that, requires the use of an ice table. Remember initial change equilibrium, those tables that we made back in our previous chapter. So a small K value, whether that's Ka or Kb, that allows us to see any changes in the initial concentration of the weak acids as negligible. Remember, we did that in our previous chapter, where if our Ka was small enough, it was less than 1 times 10 to the minus 3, then we could see any change in x, whether we were adding or subtracting x, we could see that as negligible, and that saved us from using our quadratic equation, which simplified our calculations a lot. So the result from the ice tables for our weak acids and our weak bases are what is going to allow us to solve for the H3O plus concentration, or in some cases the H plus concentration, which we know that if we have that concentration, we can find the pH. If we know the pH, we can find the pOH. If we know the pOH, we can find the OH minus concentration. If we know things at equilibrium, we can solve for Kas. We'll see how we can then use that to solve for Kbs. So again, these ice tables are just allowing us to get so much information about one solution because of how interconnected all of those values are, as we saw in our previous lessons. So let's look at a weak acid problem. Now, just because this is considered a weak acid problem, we're not going to change anything about how we're solving these ice tables. They're just regular ice tables like we saw in our previous chapter. I probably even gave you a weak acid problem with a small K value. I just didn't label it as a weak acid in Ka. I just told you it was K, and here was our reaction. So we've probably already seen many of these. We just need to now know how to identify a weak acid versus a strong acid so we know when to use an ice table and when not to. So the first type of practice problem we are going to do is using our Ka value to calculate pH. If we want to calculate pH, then we need to find the H plus concentration. So, suppose we want to determine the pH of a 0.5 molar HF hydrofluoric acid solution at 25 degrees Celsius. Now, hydrofluoric acid is not one of our strong acids. It's one of the only halogens that is not a strong acid, so just remember that one. It is the outlier there. So we know that if we take HF and react it with water, we're going to be in equilibrium with an H3O plus and F minus. Since this is a weak acid, we know it's Ka. We know that equilibrium constant from Appendix 4 in our textbook. It's also available in your ALEX data tab as well. You'll have Ka values for your weak acids there as well. So we're just going to start this problem like we do any other ice table problem. We're going to have our table. We're going to have HF. We're going to have H2O. We're going to show our equilibrium. We have H3O plus, and we have F minus. There we go. And then we have initial change equilibrium. So we set up our ice table the same way that we did in our previous chapter. Now, before we start putting in numbers, let's think about our reaction. Now we have HF, which is an aqueous, reacting with water, which is a liquid, creating two aqueous solutions. Now, if we look at our Ka expression, we know that it's going to be the concentration of H3O plus, the concentration of F minus, all over the concentration of HF. We ignore the water in our Ka. If we're ignoring the water in our Ka expression because it's a liquid, we can do the same thing in our ice table, because what's happening in the equilibrium portion or any change in water is not going to affect our equilibrium constant. Okay, remember, our ice table is telling us about concentrations. Well, we don't know the concentration of H2O because it's a pure liquid. It does not have a concentration. So anything that we put in those columns, we don't actually know. And so, since we're ignoring H2O in our Ka expression and anything at equilibrium, when we set up these ice tables, we can just black out our water column because it is not contributing to any changes in equilibrium because it's a liquid. So we have to remember that liquid is different from aqueous. Aqueous means we have something dissolved in solution. Okay, so because H2O is a pure liquid, we ignore it in our Ka expression, which means we can ignore it in our ice table. Okay, so now let's start putting in some numbers. We know initially we have a solution of 0.5 molar HF. So that's our initial concentration of HF. Before we put HF into solution, okay, our concentration of H3O plus and F minus are both 0. So we have no initial concentration of our ions in that solution just yet. Okay, so we then use our balanced equation to find our change. Since we have zeros on our product side, that means they are going to be increasing in concentration, and HF is then going to be decreasing in concentration. So we have minus X, and plus X. The one nice thing about weak acid problems is our change column is always going to be the same. I guess it's a row. It's a row. Since that hydrogen that's coming off, that's ionizing, we only do it one at a time, we're always just going to be in a 1-to-1 ratio with our weak acids. Okay, so this is always going to be set up the same way. This row is always the same. The acid that we start with is always going to decrease by a factor of X, and our ions are always going to increase by a factor of X. So you notice this actually simplifies these problems, because no matter what your weak acid is, okay, it's not going to change it. I could technically write this as HA and A minus, because no matter what that A minus is, it could be a fluorine, it could be an acetate, it could be anything. It's always going to be that one hydrogen is moving off to create H3O plus, and then the ion, the anion of the original acid. So it's always going to be the same setup. So it simplifies our ice tables a lot more. Okay, so now let's add up all of these columns. So we have 0.5 minus X, and then we have X and X. So now we can plug in our E column, our E row, to our Ka expression. So we get Ka is equal to X times X over 0.5 minus X, which we can simplify to X squared over 0.5 minus X. And we know Ka is 6.3 times 10 to the minus 4. So again, we just did what we did in our previous chapter. We just identified that this is a weak acid in this specific problem. So now we're going to do just like we did with our previous ice tables, where we are going to see this X value as negligible, and we are going to get rid of it because our Ka is small. So remember, if K is less than 1 times 10 to the minus 3, that X, that change in X, can be seen as negligible. It's only our change in X, okay, just means that there's going to be very little change in that initial concentration because the ionization of that hydrogen is very small, okay, that's why we're able to say that that X is negligible. So this simplifies our solving a lot, because now we just have X squared over 0.5 is equal to 6.3 times 10 to the minus 4. So now we can grab our calculators to solve the remainder of this problem. So in order to solve this, we're going to take 6.3 times 10 to the minus 4, and we're going to multiply that by 0.5, because I want to multiply both sides by 0.5 in order to get x alone. So we get that x squared is equal to 0.000315. And then to solve for x, we're just going to take that square root to get that x is equal to the square root of my answer. We get that x is equal to 0.017748. Okay, so this x is now telling us that this is a concentration, and that concentration is equal to not only the H3O plus concentration, but also the anion concentration. So that would go into our table as 0.0. Let's see, we have two sig figs here, 0.018 as our concentrations of H3O plus and A minus at equilibrium. Okay. Now we're not done yet. So this is where, when we're working with weak acids and weak bases, we do have to go one step further after we finish our ice table. The problem asked us to find the pH, not the H3O plus concentration. But now that we have the H3O plus concentration, we can find the pH. So what we're going to do, we know that pH is equal to the negative log of the H3O plus concentration. So we just plug in that value. Since our final answer is not that concentration of X, we can keep all of those decimal places because we'll do sig figs at the very end with pH. So we'll do negative log of our answer, and we get a pH of 1.7. Two sig figs there, so 1.7 as our final answer. So our original solution of HF that had a concentration of 0.5 has a pH of 1.7. So let's show how this is different to if we just took that concentration and used it to solve for pH. So if I treated HF as a strong acid, if I just said that, oh, I know the concentration of HF, therefore I can find the pH, we would get pH is equal to the negative log of our original concentration of 0.50. So we get negative log of 0.5. And that would mean that our pH is 0.301. So that's a pretty big difference between 1.7 and 0.301 in terms of pH. That's more than a whole pH unit away from each other. So this is why when we're working with weak acids, we have to go through our ice tables, because we can't just take that original concentration and use it to solve for pH. Now, before we move on to additional practice and additional ways to solve these problems for weak acids, I want to take a second to discuss something called percent ionization. And this has to do with the shortcut that we take in our ice tables, our approximation that X can be seen as negligible. So, the shortcut of seeing the change of X as negligible is only acceptable in ice tables here when the ratio between the equilibrium concentration of H3O plus or H plus, whichever one you use, same thing, they're interchangeable, and the initial concentration of that acid is less than 5%. So, we use our ice table to solve for our H3O plus concentration using that approximation. So we got 0.018 molar as our H3O plus concentration from our ice table. Okay, that's our 2 sig fig representation there. Okay, and that value we found using that approximation that X is small. Then we take that and we divide it by our initial concentration. We're basically seeing how small that change would be if we didn't use that approximation. So we take the ratio of those two values We multiply it by 100 to make it a percent because this is percent ionization. And that percentage is 3.6%. As long as that ratio, that percent, is less than 5, then our shortcut can be used to solve for our equilibrium concentrations appropriately. There may be some times where, yes, Ka is small, but the initial concentration is also small. So any change would actually make an effect, and that percentage would be higher than 5. If it is higher than 5, you have to go back and use the quadratic equation. Because that's basically saying that the change in X is relevant. So the ratio between the H3O plus concentration and the initial concentration of the weak acid, multiplied by 100, is called the percent ionization. Now I'm just talking about this portion of it. The less than 5% portion is relating to if we can see X as negligible. So, by our definition of acids, strong acids dissociate completely, so their percent ionization would be 100%. They would have their H3O plus concentration and their initial concentration of acid would be the same, so you would have 1/1 essentially. You would have, a value of the ratio would be 1 multiplied by 100 is 100%. Okay, so we have 100% ionization, ionization being how much of that hydrogen is ionized in that solution. Weak acids, however, only partially dissociate or only ionize partially. So the quantitative measure of the degree of ionization of a weak base is called the percent ionization. So again, here's our equation for percent ionization. Okay, where the the EQ stands for equilibrium, and the naught down there, that 0, stands for the initial concentration. So those values you can find from your ICE table because you're solving for not only your equilibrium concentrations, but you had to start with your initial concentrations. So let's practice that. Here we want to determine the pH and the percent ionization for an acetic acid solution with a concentration of 0.15 molar when the Ka of acetic acid is 1.8 times 10 to the minus 5. So acetic acid is not one of our strong acids, therefore we're going to have to do an ICE table because it's an equilibrium. Now the nice thing about weak acids and weak bases is their ionization looks the exact same no matter what weak acid you're doing. Basically what I'm saying is don't sit there and memorize all the weak acids because there's a heck of a lot more weak acids than there are strong acids. So if you know your 7 strong acids, everything else is a weak acid. And then when you go to write the equation, you don't even have to worry about the expression or the formula for that weak acid. You can just write it as HA is in equilibrium with H plus and A minus. No matter what the weak acid is going to be, that is always going to be what the dissociation looks like. A can be acetic acid. A can also be formic acid. No matter what it is, it's going to be represented in the same way. So when you're doing these, the formula doesn't matter. Okay, the formula doesn't matter. We've seen from our previous ICE tables that no matter what was reacting, we didn't care what the actual formula was as long as we had the balanced reaction. Our balanced reaction for a weak acid problem is always HA is in equilibrium with H plus and A minus. Now here I'm not showing my reaction or my reactant of water because we know that in our ice table we can ignore water. So I'm also going to ignore water in my expression here. It's just going to clean up my ice table a lot more. So no matter if you choose to use H2O as a reactant and put H3O plus as a product, or if you choose to ignore it and put H plus as a product, no matter what you do, as long as you remember that water can be ignored, your ice table is going to be the same. So now that we have that down and we know our balanced reaction for any weak acid, we can set up our ice table because we want to find the pH, which means we need to find the H plus concentration at equilibrium. Okay, so we know that our initial concentration of our weak acid is 0.15 molar. We know that at equilibrium, the H plus and the A minus concentrations are both 0. We know that for a weak acid, the change row is always going to be minus X plus X plus X. That is always the same. So now our equilibrium becomes 0.15 minus X and X and X. So now we can plug this into our Ka expression. So our Ka expression is going to be the concentration of H plus times the concentration of A minus. Again, it doesn't matter what that A minus is. You don't even have to write the formula. It saves you a lot of time over the concentration of HA. So we take Ka is equal to X times X, which is X squared, over 0.15 minus X, which is equal to our Ka of 1.8 times 10 to the minus 5. Ka is small enough so we can assume that this X is negligible. So we can simplify and call this X squared over 0.15 is equal to 1.8 times 10 to the minus 5. We can solve for X by taking 1.8 times 10 to the minus 5 and multiplying that by 0.15. So we get that X squared is equal to 2.7 times 10 to the minus 6. And then we take the square root of that value to get an X value of 0.001643. Okay, so that X value is equal to our H plus concentration as well as our A minus concentration because those are equal to each other. They're in a 1-to-1 ratio. So we know that X is going to equal both of those values. And here's where we have to go one step further now from our previous understanding of ice tables. The question did not ask us for the H plus concentrations or the equilibrium concentrations. It asked us for the pH and the percent ionization. So we have to use those equilibrium concentrations to solve for both of those values. So we know pH is going to be the negative log of that H plus concentration, 0.001643. So we get negative log of our answer, and we get a pH of 2.78. Okay, now for percent ionization is equal to the H plus concentration at equilibrium, so it's going to be that 0.001643, divided by the initial concentration of the weak acid, which was 0.15, and we'll multiply that by 100 to get a percentage. So again, that's just our ratio, our equilibrium H plus concentration over our initial concentration of that acid. So we get 0.001643 divided by 0.15, and we'll multiply that by 100. So that gives us a percent of 1.09, which is less than 5%, meaning our approximation of seeing x as negligible here in this step was perfectly acceptable, and I don't need to go back and resolve the problem. So let's continue practicing with our weak acid problems. In this problem, we're now going to use pH to solve for Ka, because pH tells us the H3O plus concentration at equilibrium, right? If we know pH, we can find H3O plus, or H plus, whatever, whichever one you want to use, by taking 10 to the negative pH. So if I know pH, I know that portion of my ice table. Just like in our previous chapter when we had information about the equilibrium concentration, we could use that to find our K expression or our K value. And that's exactly what we're doing here. We're just adding an extra step in order to find that equilibrium concentration. So again, these are problems that you've done before. We just have to take maybe an extra step at the end or an extra step at the beginning now that we have this new knowledge about acids and bases. So let's practice that. Here we want to determine the Ka of a weak acid that has a concentration of 0.25 molar and a pH of 3.47 at 25 degrees Celsius. So again, it doesn't matter what the weak acid is because our dissociation is always going to look exactly the same. Again, it doesn't matter what this A is, we only care about where this hydrogen is moving. So we can use our generic equation here. I've included water here. You don't have to include water. You can show HA is in equilibrium with H plus and A minus. That's totally fine, whichever one you want to do, okay? So let's fill out our ice table here. We know that water is not going to contribute, so we can just get rid of that column. We can just black it out so we know we're not going to put anything there. We know our initial concentration of the weak acid, and that is 0.25 molar. We know that our initial concentration of H3O plus and A minus are both 0. Our change row is always the same, minus x plus x plus x. So we get 0.25 minus x, x, and x. So we're solving now for Ka. So we know from our pH, we know what x equals. So what we're going to do first, we want to solve for x. So in order to solve for x, we're going to take the pH and do 10 raised to the negative pH, 3.47. Because that's going to give us the H3O plus concentration. So 10 raised to the negative 3.47. And we get, we'll put that in scientific notation, 3.388 times 10 to the minus 4. So that is our H3O plus concentration, as well as our A minus concentration. So we can now take this value and say, okay, well, we know this now for this x. We know it now for this x. We can also plug it in for that x there, and even solve it for that as well. So now that we know what x is, we can solve for Ka. So we know that Ka is going to be x squared, so 3.388 times 10 to the minus 4, that's going to be a squared value. X times x is x squared, divided by 0.25 minus that x value. Since we don't know the extent or how big or small Ka is because we're solving for it, we can't use our approximation that x is small. Will it most likely be small and very rarely change your Ka value? Sure, but since you don't know the value of Ka, you cannot make that assumption. So you still have to plug that x value in. Okay, so now we just solve for Ka. We just do that math. Again, just like we did in our previous examples of ice tables back in our previous chapter where we were looking for K. Now we're just looking for a specific K. So we're going to take 3.388 times 10 to the minus 4. We're going to square that value. And then we are going to take it and divide it by 0.25 minus 3.388 times 10 to the minus 4. Just using parentheses to make sure I'm dividing and subtracting the right numbers. So we get that Ka is 4.59, let's call it 60 for sig figs and rounding, times 10 to the minus 7 as our Ka value. So we worked backwards. We knew pH. That gave us information about our equilibrium concentration of H3O+. So we already could find X by just doing 10 to the negative pH. Okay, that gave us the H3O+ concentration. If we know X, we can find all of our values for our concentrations at equilibrium, which we then plug in to our Ka expression for that balanced reaction. And we get a Ka of 4.60 times 10 to the minus 7. So now let's talk about weak bases. With weak bases, we can use the same approach as with weak acids to solve problems that involve weak bases. It's the same concept. It's still an equilibrium expression. It's still an ice table that you have to complete. The only thing that you have to remember is the difference between acids and bases and the information that they provide. So remember that if we have the ionization when it comes to a base, the hydrogen from the water is now going to be moving over to that base, creating Hb plus and OH minus. So unlike our weak acids, we don't have a simplified version of that equation, so we do have to show water just to show where the hydrogen is moving and coming from. But as long as you remember that water doesn't contribute to those ice tables, you can just cross out that column when you get to it. So our Kb expression is now the concentration of the Hb plus and the OH minus over the initial concentration of the weak base. You can still use the B notation. You don't have to put in the entire formula like we did with our weak acid. Again, because there's a lot more weak bases than there are strong bases. So instead of worrying about what the formula is and memorizing those formulas, just use the B notation because, again, the dissociation is still generic no matter what that base is. We're still going to have a hydrogen move from the water and go to the base with a positive charge, and then we're going to have an OH minus on there. So the Kb here, now the B stands for the base ionization constant or the equilibrium constant. But again, the larger the value of Kb, the stronger the base is for the same reasons as acids as we discussed earlier. So let's solve a problem for a weak base. When we're working with weak bases, we have to remember that the pH is calculated from the hydronium ion concentration, and the pOH is from the hydroxide. So in our equation, in our generic equation, or if we have the balanced equation for the specific base, we're always going to get out the OH minus concentration. So we have to use our knowledge of how pH and pOH relate to each other to find the correct value. So again, always look at what the problem is asking for. If it's asking for pH, then we have to remember that we're getting the OH minus concentration, which means we can find pOH, which means we can then subtract that from 14 to find pH. If it's just asking for the pOH, then you don't have to do that last step. So just look out for what the problem is asking for you to do specifically. So here we want to know the pH of a 0.04 molar ammonia solution at 25 degrees Celsius. Okay, so we have our balanced equation here. And again, we're going to treat this just like we did our weak acid problem. Again, it's just a regular equilibrium problem. So we're going to set up our ice table. We're going to ignore water because it doesn't contribute. We know the initial concentration of ammonia is 0.040. The initial concentration of our products is 0. The change column is just like our weak acids, minus X, and plus X. Okay, that's still the same. They're still changing in the same way. And then we find our equilibrium, 0.040 minus X, and X. We can set up our Kb expression. We know Kb is going to be the concentration of the NH4 times the concentration of the OH minus over the concentration of the NH3. We can use Appendix 4 to find the Kb for ammonia. So Kb for ammonia, if you look in Appendix 4, is 1.8 times 10 to the minus 5. So we see that Kb is small. Again, it's just like our previous assumptions with K. If it's small, we can see that X as negligible. So we know that Kb is going to be equal to X squared over 0.040 minus X. We can see that X as negligible, so you get X squared over 0.040 is equal to our Kb of 1.8 times 10 to the minus 5. And we solve for X accordingly. So we'll take that 1.8 times 10 to the minus 5. We'll multiply it by 0.04, so we get X on one side. We get that X squared is equal to 7.2 times 10 to the minus 7. And then we'll take the square root of that value to solve for X. So we get X is 8.48 times 10 to the minus 4 molar. Now that concentration is the OH minus concentration. It's also the NH4 concentration. We're not done yet because the problem asked us to find the pH. You can find the pH in two different ways. You can take the OH minus concentration and you can use that to find pOH, and then you can do 14 minus that pOH to find pH. Or you can use the OH minus concentration and Kw and use that to find the H3O plus concentration because this reaction is at 25 degrees Celsius. Okay, we've done that in a previous lesson. If we know OH minus and we know Kw, we can find the H3O plus concentration, then use that concentration to find the pH. Again, we showed in our previous lessons that no matter which way you go, it'll all give the same numbers because they're all related to each other. So let's take the first route. So we are going to do, let's do it over here. pOH is equal to the negative log of our concentration, 8.48 times 10 to the minus 4. So we'll do negative log of that answer. Oops. And we get that the pOH is equal to 3.07. So we'll do 14 minus that value to get the pH of 10.92. 93 with rounding. There we go. So again, these are just like our regular equilibrium problems. We just now have to take some extra steps with our new knowledge of acids and bases. Specifically, the difference between a weak acid and a weak base is that the weak base is going to provide us with the OH minus concentration, and the weak acid is going to provide us the H plus concentration. So depending on what the problem is asking for, pH, pOH, or any specific concentrations, you have to then plan accordingly with your knowledge of pH and pOH and how they relate to each other. So now let's discuss the relationship between all of our equilibrium constants that we have introduced in this chapter. So we've talked about Ka, we've talked about Kb, which are the equilibrium constants for a weak acid and a weak base. Then we also talked about Kw, which is the equilibrium constant for the auto-ionization of water. So they do relate to each other because Bronsted acids and bases cover the transfer of protons. Therefore, there is a relationship between the strength of those acid-base conjugate pairs. So, for any conjugate acid-base pair, let's say we're talking about just HA and A-, okay, our first expression, we're going to take HA, react it with water, and get H3O plus and A-. Then we can say, well, what if this A minus then participates in a reaction, right? Because this can now act as a base. It's the conjugate base to the HA acid. So since the conjugate base, it can now act as a base, reacting with the additional water that's in that solution, creating the OH minus concentration as well as the original acid that you started with. Okay, so there is a relationship between those two expressions, just using one conjugate acid-base pairing. Now, if we take those two equations, okay, that HA plus H2O and the A minus plus H2O, if we add them up, similar to how we do in Hess's law, okay, if we add both of these up, we get HA plus H2O plus A minus plus H2O is in equilibrium with H3O plus A minus plus OH minus plus HA. And as we know from Hess's law, anything that's the same on opposite sides of the arrow can be canceled out. So A minus can be canceled out, HA can be canceled out. And we're left with the equation 2H2O is in equilibrium with H3O plus and OH minus. So the sum of those two equations, those two reactions from one acid-base conjugate pair, is just the reaction of water, the auto-ionization of water. We know what that expression is. We can say that Kw is equal to H3O plus and OH minus. We know that. That's just the auto-ionization of water. However, we can use those two equilibrium constants of the acid and the base reaction, and we can multiply them together because the equilibrium constants for a summed reaction is equal to the product of the equilibrium constants for the added reactions. So we can see here that Ka times Kb is equal to H3O plus times HA, or times A over HA multiplied by HA times OH minus divided by A minus. So we can see that those A minuses will cancel, the HAs will cancel, just like they did in the balanced equation. And we're left with the H3O plus concentration and the OH minus concentration, which again gives us our Kw expression. So the relationship between Kw and Ka is that Kw is equal to Ka times Kb. So if you know a Ka at 25 degrees Celsius and you need to find a Kb, then you need to use this expression. Appendix 4 in your textbook only gives Ka values. Even for bases, it gives you a Ka. It does not give you a Kb. So if you went to Appendix 4 to find a Ka value, or to find a Kb value, you would not find it. You could find it by taking the Ka from Appendix 4 and using it with Kw, which we know is 1.0 times 10 to the minus 14. So you could just solve for Ka or Kb, depending on which one that you need. So the equation Ka times Kb is equal to Kw states the relationship between any conjugate acid or base pair and says that it's equal to the ion product of water, Kw. So by rearranging this equation, the reciprocal relationship between the strengths of the conjugate acid-base pair becomes evident. So if you wanted to find Ka, you would take Kw and divide it by the Kb. Or if you wanted to find Kb, you would take the Kw and divide it by Ka. Again, because Kw is equal to Ka times Kb. So let's practice that. The Kb for a nitrite ion, an NO2 minus, is 2.17 times 10 to the minus 11. Calculate the Ka for this conjugate acid, and let's say that this is at 25 degrees Celsius, because then we know our Kw. So again, Kw is equal to Ka times KB. Here we know Kw is 1.0 times 10 to the minus 14. We're looking for Ka, and we know Kb is 2.17. So that's a 4. 7 times 10 to the minus 11. So we take Kw and we divide it by Kb. And we get that the Ka is equal to 4.61 times 10 to the minus 4. And that's how we can use our relationship between Ka and Kb and Kw to find our unknown value of Ka. Now, in your note packet, you have 3 additional problems that are specifically practice problems with weak acids and weak bases, using pH, pOH to find concentrations or to find Kas or to find Kbs and percent ionizations. So what I want you to do is to practice those 3 problems independently. I will not be going through those in this lecture, but you are required to complete those for full credit in your submission. The answers will be posted on e-learning so that you can check your work to make sure that you got it correct before going on to your homework and your exams, and then you can use that to correct what you did wrong to then learn from those mistakes. So work on those 3 problems independently. Once you complete those, you can check your answers on e-learning.